Hi TAs and professors, this is Team 7 attempting to redo our demonstration. I'm Jamie.
I'm Terrence.
I'm Fang.
And our project is a cheaper alternative for a room scale 3D LiDAR system. So we have our project over here. A LiDAR system acts similar to a radar, but instead of radio waves, it uses lasers of around 400 millimeter wavelengths. So yeah, I'll hand it over to Terrence to talk about how it works.
Alright, so the way that our system is designed, it uses a TOF time of flight sensor which measures point-to-point distance. It's rotated horizontally and vertically. Horizontally 360 degrees for each cycle. Every cycle that passes, the vertical motor pitches up by a set amount of degrees, and it results in a point cloud, a bunch of point cloud data. That point cloud data is sent via Arduino, is collected on Arduino in the microcontroller, and then sent to the computer where it's then parsed and then encoded into file format for further viewing.
Yeah, now I'm going to talk about the high-level requirements for our project. First of all, our project is going to rotate horizontally in 360 degrees and vertically in 60 degrees. Secondly, the microcontroller in our system should be able to communicate with the sensor, and the sensor will transfer the one-to-one distance data, point-to-point distance data to the microcontroller, and the Python program should be able to take the data from the microcontroller and output that into a 4,000 point cloud output, which is in our AS file, and AS file is industry for my file.
Alright, now that we've ran through the procedures for a normal demo, let's talk about why our project isn't fully functional at the time of the actual demo. So first of all, 10 minutes before the actual demo, when we started packing the project to move into the ECE lab, our project is fully functional. When we went to the ECE lab and plugged in the 12-volt power supply, we noticed that the stepper motor driver is unusually hot. When we went home and took out the stepper motor driver to individually test the module, we have determined that indeed is the point of failure. We couldn't put our hands on exactly why the stepper motor driver failed the way it did. One possible reason could be some unnoticed short when we plug in the driver, or another potential reason is that there might be a power surge when we plugged in the 12-volt power supply, and that might have exceeded the tolerable voltage of our chip. Now that we've talked about why it could have failed, let's talk about what we have done. So in terms of functionalities, the only thing we have done is to swap out the stepper motor module with a new one. That has fixed all the functionality, and after that, our project can work properly. There are two other modifications we did that does not affect the functionality. One of which is to add this shield to protect the sensor from the elements. And the other one is to print out a more robust shell compared to the one during our actual demo day. Both elements does not affect the functionality. And that is all that we have done to bring our project up to the level of polishedness that we desired. Right now we'll show the functionality of our project. So two things needs to be plugged in first: the 12-volt power supply and the micro USB cable. And after all that is done, all I need to do is run the Python script we have over here. So I have asked two of my partners to hold up picture frames as requested by the professor, so that we have features to try and recognize in the end. Three features to keep in mind is the two picture frames being held up by my friends, and also the really large curved monitor to my right and your left. So after we scan, we're going to insert a video of 300-degree rotation from the point of view of our LiDAR sensor so that you can try and make correlations between our data and the video data that we will provide. So right now we will restart and run all for the program, and we just wait. Now that we have done that, the Python code should have outputted it into a file called LiDAR.las, and then there should also be verifications being run on terminal, which is done over here. Okay, so now that we have scanned the file and it has inputted the stream from the microcontroller, converted the string data into NumPy arrays, did the spherical to Cartesian coordinate conversions, and outputted the files as LiDAR.las file, and also validated it, we can see in the terminal that it says reading file, 0 error out of 4 tests. If there are any unexpected data, one of the tests would have failed, as if the data does not make sense, then one of the tests would have failed. So the last thing we need to do is to open Cloud Compare, which is one of the software that can view a LAS file, and dragging the LAS file. Okay, now that this file is imported, we can see that the top-down view is really intuitive and is indeed the layout of my room. Even the indentations of the windows are clearly visible. Once we start orienting the room in desired orientation, we can see that there are 2 chairs over here, as according to the video I am going to show, the curved monitor, and Xijin, which is one of my partner, holding up one of the features. You can even see the diagonal position of his arm, which is quite surprising. Terrence's feature is over here behind the wall, which is quite hard to make out. But you can see from the background that this part is indeed cut out, which means all the points flying into this position is registered before the ray hits the wall, and this array of files, this array of points should correspond to this feature. Like I said, this point cloud file consists of 4,000 points, and if time is permitted and we are allowed to increase the accuracy and decrease the time running, we could get an even more detailed view of the room.